Geometry in and of itself is a very vocabulary intensive mathematics because a lot of geometry is about how things are defined or described, whether or not they can be defined. We have a bunch of theories, we have postulates, so there's a lot of vocabulary that you don't have to. We're adding undefined terms. They can only be described but not actually defined. Kind of like you can't define a person, but you can describe a person. Does that make sense? Okay, so an undefined term can only be described, not defined, and I'm going to put a little asterisk on the terms here that are undefined or considered undefined. Okay, so these three terms that I'm about to describe for you, these are not technically definitions, they're descriptions. Postulates are statements that are accepted as true. We accept them, but we don't need proof for them. They're things that just make sense. Okay. I call them, like, well, duh statements. Okay. You guys are all familiar with 3D? Yes, 3D, three-dimensional. There are multiple dimensions. There's 3D, which we are 3D because we're three-dimensional. There's 2D, 1D. There's zero-dimensional. And then you can actually go the other way too. There's 4 dimensions, 5 dimensions, 6 dimensions. We just can't see them because they're above us because we're three-dimensional. So we can't see like 4 dimensions, but we can see the dimensions that are below us. A piece of paper is 2-dimensional, it's flat. We can see that. A point has no dimensions. It's 0-dimensional. It does not have shape and it does not have size. Now we draw a dot to represent it, but this dot is huge compared to what a real point is. If you think about atoms, right? And atoms are made up of protons and neutrons and electrons. And then you think about the subatomic particles that make up the protons and neutrons and electrons. You're starting to get to be as small as a point is. They're beyond microscopically tiny. They have no shape and no size. They just represent a location in space. And I know that's kind of hard to really comprehend, but they're just that tiny. And because they have no shape and no size, they have no dimension. Does that make sense? So that's why they're 0-dimensional. Okay, a line is 1-dimensional. And a line is an infinite string of points. So if I take these little tiny points and I connect them together dot by dot by dot by dot by dot forever, just an infinite number of them, I get a line. Okay. And they go on in 2 directions. So they're infinite. It's an infinite string of points in 2 directions. And we represent a line by drawing, well, a line with arrows on the end of it because it's infinite and it goes on forever and ever in both directions. And the points are so small that even in this little tiny chunk of line I drew, there's an infinite number of them. Plane is 2 dimensions. And a plane is an infinite collection of points. In all directions. Okay. So if you think of the piece of paper, and I said a piece of paper was two-dimensional, if you could take that piece of paper and you could stretch it and just make it bigger and bigger and bigger and bigger forever, that's a plane. Like, it would never end. It would just be a never-ending piece of paper. Completely flat, but going on and on forever in that flatness. Does that make sense? Kind of? Okay. We can represent it in two ways. We can either do the two axes, draw that a little better. Two axes like you're used to with the coordinate plane. Or we draw a parallelogram to represent the piece of paper that's continuing forever. Okay, collinear. Collinear is just a word that means lying on the same line, and it's points. Okay, and if you are not collinear, so the opposite, you are non-collinear. Coplanar is points or lines lying on the same plane. And if you are not coplanar, you are non-coplanar. Okay. Now, a point can lie on a line, but a line can't lie on a line, and a plane can't lie on a line. Does that make sense? It's sort of like a flea could lay on you, but you couldn't lay on a flea. Like, it wouldn't be able to hold you, right? Because it's too small. But it can fit on you, but you can't fit on it. That's the same thing. A point can be on a line, but a plane can't be on a line. So that's why only points can be collinear. But when you get to coplanar, both points and lines will fit on a plane. So you can have points and lines that are coplanar to each other or whatever. Okay, and then space. This term is defined, and it is defined as the boundless, three-dimensional set of all points. And it contains points, lines, and planes. And you think of geometric space as the same thing as outer space. It just goes on and on forever in all directions without end. Does that make sense? It's, if you talk about like the geometry space that we're talking about, it's the same thing as like outer space. Like, it just keeps going on forever, everywhere, in all directions. So I don't know which one got named first, but I imagine one of them, they were named after each other. Like outer space and geometry space, I think they were, you know. Large part of geometry is going to be interpreting pictures into words and taking words and turning them into pictures to be able to solve these problems. And in order to do that, we have to know how everything is named. Just go ahead and just rip it. You're fine. Oh, no, go ahead. Okay, so we have to figure out how things are named so that you can go, excuse me, go back and forth between the pictures and the words and understand what everything means. Okay, so if you're talking about a line, there are two ways to name a line. One is, do you see how this line has points on it? But then it has this letter here with no point? So there's no point. So that is the name of that line. That is one of the names of that line. So we could call this line N. Okay. If it has a dot, it's a point. If it has no dot and it's italicized, it's a name. The other way that you can name a line is by using any two letters which are points, any 2 points on the line. So this line N that contains point W could have a bunch of names. I could call it VW, and then you put this symbol on top of it, that indicates it's a line. Okay. I could call it WX. I could call it XY. So I can use any two of these points. Okay. So to name lines, you can either use the little italicized letter if there is one, that's not a point, or you can use any two letters that are points on the line. Okay, to name a plane, there's two ways to name a plane as well. If you have, see this P has no dot? If there's a letter in a corner of the parallelogram with no dot, that's the name of the plane. So if there's no dot and it's in the corner, it's a name. So I can call this plane P. Okay. Or I can use any three of these other letters over here to name the plane. Lines need 2 letters, planes need 3. So I could call this plane XYZ, right? Because I have XYZ. I could call it plane VWX. Just any 3 letters. The only thing I cannot use is T, because as you can see, T is way up here. It's not on the plane. Okay. There's not a symbol to use for plane. You have to actually write out the word plane, unfortunately. Like here we have the line, but we don't have one for this. Okay. If we want to name a plane containing points T and Z. T and Z connect with this line here. To make sure I get a plane that contains both T and Z, I need to find another collinear point with one of those 2 letters. Yeah, X. So it has to be either collinear with T or collinear with Z. And in this case, it's going to be X because it's collinear with T. So I'm going to call that plane. I could call it TXZ, or I could say XZT, whatever. The order of the letters on planes does not matter. We're going to get into other things that naming them, the order of the letters really is very important, but in a line and a plane, it doesn't matter. Just any 2 letters makes the line, any 3 letters makes the plane. Okay, if I talk about the line containing point T, this line here, there's 2 ways I could name it. See that little R right there with no dot? So I could call it line R. Or it has an X and a T on it, so I could call it line XT. Whoops, I didn't mean to write the word line there. call it xt, or I could say tx. What I can't do is use these v, w, y, or z because they're not on that same line. And this line I drew, tz, doesn't actually exist in the picture, so we can't use it. Oops, I had erased my points. Oh, that's way too big. Picky now. Is the set of all points that, I should say two or more, geometric figures have in common. So they're the overlap between two things. If we look at two lines, this is the intersection, and it's a point. Okay. Our lines are one-dimensional. Our intersection is zero-dimensional. Does that make sense? Two lines can intersect at a point, like this, or they can intersect at a line. And to show you what that looks like, if I have my first line is black and my second line is red, it's the same line basically. What you've got is you've got two lines laying on top of each other, so they're intersecting at all points, they're intersecting into a line. What you can't have though is you can't have two lines intersect and that intersection ends up being a plane, because you can only intersect at what you are or smaller. Does that make sense? Here we have two planes intersecting. And they form a line. So basically this is two pieces of paper going through each other and it makes a line. Or here we have a line and a plane. And they're intersecting at a point. Because it's like an arrow going through the paper, but that creates a point. So intersections can be points, lines, and planes as well. I can have two planes intersect at a plane if I take, well, this stack of paper. If these are all planes, they're all intersecting in two planes because they're on top of each other. Does that make sense? And to do that, first, just read everything first. So I have lines A, B, and C, D intersect at E. I have coordinates for A, B, C, and D on a coordinate plane. Point F is coplanar, but not collinear with line A, B, or C, D. Okay. So the very first thing I'm going to do is, I've been given specific information for A, B, C, and D, so I'm going to do that first. I'm going to plot A, B, C, and D. So I'm going to do line AB in blue, and I'm going to do line CD in red, just to differentiate. You don't have to do that ever, but oh. Alright, so I'm going to start with point A, which is at -2, 4. And then point B is at 0, -2. Okay, and that's a line. I know that's line AB, so I'm going to go ahead and connect the dots. Okay, so there's my line AB. And then I have C. Point C is at negative 3, 0. And D is at 3, 3. Okay. So I plotted point C and D. That was C. And there's D. And I'm going to connect those lines. Okay. And I was told that it intersects at E. So here's the intersection. So I'm going to label that E. Okay. And then the final thing I know is that F is coplanar. Well, this is a coordinate plane, so it's a plane. So coplanar with these points, but not collinear. What this tells me anywhere has a Y in it. Okay, I have two lines and I have a bunch of space. Because F is coplanar but not collinear, I can put F anywhere except on a line. So there's a bunch of places. I mean, F could go anywhere in this section, anywhere here, it doesn't matter where. So I could put that right there and call it F. I could have just as easily put it over here and called it. I don't even have to put it on a specific coordinate, because in between 3 and 4 there's all the decimals, right? So this whole thing, I could put F smack dab in the middle of a square if I want to. It doesn't matter, just so long as it's not on a line. If we look at B, I have line QR is intersecting plane T at point S. If a line is intersecting a plane at a point, that means that the line goes through the plane. Okay, so this tells me the line is going through the plane. If a line intersects at a line, it's laying on the plane. Okay, so first I'm going to draw a plane. And to represent a plane, we draw parallelograms. They don't have to be perfect, but I kind of like mine to be perfect, so I cheat. Okay, and I want to call this plane T. To name a plane a letter, it can go at any of the four corners. You just don't put a point. It's just a letter without a point. So it could just go there, or it could easily go here, here, or here. Okay, so this is now plane T. Line QR is going to intersect the plane at point S. I could do this two ways. I could draw a line through the plane and then find the place where it intersects and call that point S, or I could draw point S and then draw a line through that intersecting the plane. What do you guys want to do? Line first and then label the point, or point first and then draw a line through it?
Let's draw a line.
Okay. When you're drawing a line intersecting through a parallelogram, it can go straight up and down, it can come in sideways, however. What you want to do is at some point you have to switch from being a solid line to doing a dotted line. Okay? That tells me that this is going through the plane. Okay? Now we know that it intersects at point S, so at that point where I switch from solid to dotted, I'm just going to say that's S. It's a line, so I need to put arrows on both ends. And it's line QR. So I need to label this with a Q and an R somewhere on it. But it doesn't matter where. I could put Q up here, and I could put R down here, or I could put Q and R both up here. As long as there's a Q and an R somewhere on the line, they can go anywhere. So Q and R can go anywhere on the line. But S has to be at the intersection. Okay. On this one, we don't have any graph paper. I didn't put a graph on here, so I did that. I want to show you what to do if you have no graph paper and you need to do a problem like this. I'm going to try to draw a straighter line than that, but whatever. I'm going to draw 2 axes. And then I'm going to make tick marks and try to get them, relatively the same distance apart, but if it's not perfect, whatever. It'll represent still what you're trying to do. Okay. Point J is at -4, 2, so I go -4 up 2. Call that J. And point K is at 3, 2, 1, 2, 3, up 2. Call that K. Points J, K, and L are collinear, so that tells me I need to draw a line through J and K. And L. Unless you're specifically told, like L comes between J and K, or L is to the left of K or something like that, it can go anywhere. So we can go JKL and be alphabetical, or we could put L over here before J, or we could put it in the middle, it doesn't matter. Just somewhere on the line, because it's collinear. And finally, we're going to have line P lies in plane N and contains point L. So I'm going to start by drawing a plane. And I'm going to call that plane N because they said to. Line P lies in plane N. Before we were intersecting, so we did this dotted cut through thing. If your line lies in the plane, you don't want to go past the boundaries of the plane. This indicates that the line is in the plane, it's on the plane. If I go past the boundaries, it could be an intersection that I just didn't dash properly. So if you're on the plane, you want to keep it in the boundaries of the picture. Okay. And it contains point, first of all, it's line P. Just don't put a dot and you've named your line. And it contains point L. It can go anywhere on that line. When I look at this kind of a drawing and I'm asked how many planes appear in the figure, it's kind of almost a trick question because your first gut response might be 1, right? Yeah? Okay, cool. Because we have the 1 here, but then each side of this pyramid is also a plane. These planes take 3 letters to define, and each side of the pyramid is a triangle, so they have 3 letters. So they're all planes. So when I look at this, okay, the bottom of the pyramid is on top of the parallelogram plane, so that's the same plane. That one doesn't count twice. So I need the big plane and I need the sides of the pyramid. So there's 1, 2, 3, 4, 5, 6 sides. And then the plane that's the bottom, so there's 7 planes. Okay. I need to name them all. Well, this one has its name, plane X. And then I'll need to name each of the sides of the pyramid using the 3 letters that make up the triangle. So I have J, H, and D, J, K, and D, okay, K, E, and D, E, F, and D, F, G, and D, and then G, H, and D. And I've got all 7. That part okay? All right. 3 collinear points. So I need 3 points that are on a straight line. Yeah. Yeah, J, C, and D. That's the only one where we have them all on the same line, right? So. We have plane HDG. That's this front of the pyramid. And it's intersecting plane H. And it's intersecting it. A plane is intersecting a plane at a line, right? It's not a very good line. There, that line. Do you see that intersection there? Nod yes or shift your head no. So the intersection, I can name it line HG. Okay. At what point do line AB and line EF intersect? Well, EF is lying on this plane, isn't it? So EF is hanging out, kind of, going this way. AB is cutting through the plane here. So it's hanging out over here doing this. They're never going to meet, are they? So they're not going to intersect. So you would just say no intersection. Okay. Then we have our points E, D, F, and G coplanar. Well, E, D, and F are on a plane together, and E, F, and G are on a plane together, and D, F, and G are on a plane together, but are all 4 of them ever on the same plane? No, right? Because of this angle here. If F was in a straight line with G and E, then it would work, but because there's that angle, we can't make a plane where all 4 of them will ever be on the same plane. So, no. And then finally, at what point or in what line do planes JDH, JDE, and EDF intersect? So, JDH, JDE, that would be a plane if we drew across here. Kind of a triangle cutting through the middle of the pyramid. Do you see that? And then EDF. Where's the only place that all of those hit? D. So it's at point D.